Okay, welcome everyone to the industry guest lecture of CSE 132C database system implementation. It's a pleasure to introduce Hannes. Hannes is a senior researcher and acting group leader in the database architectures group at the Centrum Wiskunde and Informatica, CWI in Amsterdam. Hope I pronounced it right. And he's a co-creator of the novel DuckDB database management system and co-founder and CEO of DuckDB Labs, a CWI spin-off around the DuckDB system. Hannes' research interests revolve around in-process analytical systems. So I've heard a lot about DuckDB in the last couple of years, so I was really curious to learn more about their kind of what they're building and their trajectory. Thank you for joining us, Hannes. And let me guess, your last name is pronounced Mühleisen. Is that correct?
Pretty good.
Okay, got it. I'm trying to learn some German too.
Mühleisen, but yeah, that's
Mühleisen. Okay,
advanced.
Sounds good. Okay, take it away. So Hannes, do you mind questions during, or do you want to keep it till the end?
No, I think it's a great idea if people have questions to just interrupt me and ask. It's difficult for me to see the chat while presenting slides. So Aaron, if you can, like, if somebody asks a question in chat, if you can alert me to that would be great. But otherwise, yeah, just talk to me. I'm far away. I can't do anything dangerous to you from here. So that's, you don't have to be concerned about asking questions.
I'll monitor the chat for you. Audience, if you have questions, feel free to unmute and speak and interrupt Hannes whenever. Take it away. Right. Thank you.
Thank you. I just have a minor issue that I have a pop-up window from Zoom in front of my slides. So just a second, I have to get rid of that.
Oh, sure.
There we go. Okay, great. I can start?
Yes, you can start.
Excellent. Hello, everybody. Welcome to my talk. My name is Hannes Mühleisen, as Aaron has said. And I have many hats, but two of them are the co-founder and CEO of DuckDB Labs and senior researcher at the CWI Database Architectures Group. The CWI, not many people know about it because it's a small thing from Holland, is the place where Python was invented. It's the National Research Lab for Computer Science and Mathematics of the Netherlands, located in beautiful Amsterdam. If you wonder where I am at the moment, this is my floating home office. It's this red, big, giant steel box, and I'm where the arrow points, and this is actually underwater. So if you see sort of me panicky running around, then that's why. Let me start my lecture today a bit on reflections on client server, because client server is something that is so widespread and obvious to everyone that we rarely question it, but it is actually not something that is like, God-given, or if you want, or anything like that. So client server is this architectural pattern that we say we'll have the database server runs on like some computer somewhere, today often in the cloud, and we have a client program sitting like somewhere else usually on your computer or on the applications like servers. And then there's a sort of client protocol between. This has not always been the case. It might come to a shock to some people. So in 1974, for example, it was totally common to talk to your database server using a mainframe terminal, which is this old school thing where you have your server and you only talk over a serial or so connection. And it basically renders a screen for you when you type in it, but everything happens on the server. Not really a client server setup, right? It's a mainframe thing. And only in 1984, which is coincidentally the year I was born, did people start in Sybase, as far as I could tell, to implement a client server setup with this whole separation of client program and client protocol and server program and server protocol, the whole. But for example, when you run like Postgres, you will have your Postgres server and you have your Postgres client, and they need to talk to each other and so on and so forth. Obviously, as it's the way with technology, we had a swing back. So in 1994, BerkeleyDB came out, which is still a very popular system. It's, I think, at this point owned by Oracle. And this is like really I think the first sort of purpose-built in-process database management system, although without actual SQL support. It's more like a key value interface before it was a thing. And in 2000, we get SQLite, which, in case you're not aware, is the world's most popular database management system with, according to the creator of SQLite, about 1 trillion active databases, which is a lot. And so you can see from this timeline that this whole client server thing may not always have been the case, and it's also it's kind of iterating between like being a thing and not being a thing. If we try to kind of look at the landscape in a different way, by adding the separation between transactional systems, OLTP, and analytical systems, OLAP, OLAP, you can see that if we just list open source systems, you can see that there is also a bit of a gap there. So we have in-process OLTP systems, that is SQLite, it's extremely good at being that. We have a standalone like client-server OLTP systems like Postgres, and we have standalone OLAP systems like ClickHouse. But there is not really anything that I can think of, at least in the past, that was filling this empty space up there, which is the in-process OLAP. And why is in-process OLAP a good thing? Well, allow me to do some more sort of, let's say, theoretical slide here, where if we look a bit at this whole machine learning, analytics, whatever you want to call it, and data management, we often have this perception that we have this database, sort of the central sun or something around which everything revolves. And then there's this also this ML thing, which sort of somehow in the orbit to it. And people think, at least in the database community a lot, and I know that Arun has been working on that as well, but I think the overall observation is that people think that ML is just one of these things that eventually will be tacked onto database management systems. I think that's not going to happen. I think what's going to happen is that these systems are just going to grow, these ML systems are just going to grow independently and probably reinvent a lot of things that is now a part of data management architecture. Basically, my fear as a very diehard and convinced data management systems fan is that but the databases will eventually sort of fade into obscurity, something that is used maybe by IBM. So from that, I think we should conclude that we should integrate with kind of the world around data systems and not try to absorb everything. It's a bit like this, you know, the big blob trying to absorb everything, and I don't think it's gonna happen. And then back on this client server thing, the problem with client server is that it ruins this database learning marriage, if you want, because you cannot transfer serious data amounts using client server protocols. The perception is that, well, this is not a problem really, because we have this client server stuff and it's like custom built protocols and they are very, very fast at transferring data. And the reality is, no, this is not the case. We wrote a paper about this some years back, that these database protocols, they're just really, really bad. And they're so bad that you'll be better off in many, many cases just writing to a CSV file and then reading the CSV and then copying the CSV file over the socket with like SCP. And then on the other side, reading the CSV file again, that really cannot be the answer. And there is some movement in this space. So we work a bit with the Voltron Data Arrow people, and they're working very hard on improving this, but the status quo is still that the protocols that are spoken between database clients and database servers are still bad. And the conclusion from that is that if you try to convince people to use data management systems and then they try it and they realize that they spend all of their time transferring data to and from it, then they may be better off using something else. They may be better off removing these like bottlenecks in their systems altogether. And let's maybe not let it come to that. InProcess one anyway. So this is a slide. This is something that I got from the SQLite website. Yeah, he's slightly, Dr. Hip is like slightly braggy here when he says like, yeah, it's used more than all other database engines combined. SQLite, the world's most deployed database management system, it's in process. It doesn't have a client protocol. It's just database as a library. It's you can put it into anything, and in fact, people have it's running on your phone in like 15 copies right now. probably even Zoom links to it. It would really not surprise me. Yeah, so trillions in-process one anyway, sort of this architecture war is kind of over. It's not only my opinion, like Sigma Systems Award was recently given to SQLite because it has been so influential. So why is in-process great for analytics? Well, because you can do some interesting things. For example, if you want to share data between two things running in the same process, it's quite easy. You just point to a pointer. So if the data is in memory, somebody allocates some memory, writes some stuff to it, and then if you want to hand it over to some other piece of software running in the same process, you can just say, hey, here, this pointer, there's some data there, here's the layout, like go figure it out. That's really nice. We can even do zero copy. We can even say, hey, database system, I want you to read some data, but it's actually over there. And you can just run scan it as if it were a table without ever copying it. So it's very powerful. People underestimate how much people hate to manage services. So if you don't have a server to manage, even if it's on the same machine, like if you don't have to run a Postgres instance and then make sure that the Postgres is actually running before you start your scripts, like this is like a whole bottle of nightmares. If you don't have to do that, that's really excellent. If your database is just in a file, a single file even that you can maybe email around, then that really becomes a completely new way of thinking about data systems. Installation is very much simplified because, again, how do you install an in-process database management system? Well, you link to it. You do this during build of whatever application hosts the system, and that is just there. You don't have to install anything. It's just baked into the binary. You get very nice script portability because, for example, if you have like a Python script that runs some data analysis, if that was to talk to a local Postgres server, yeah, you could do it, but then probably somebody else installs this on some other box, and the default username will be different. The default password is probably going to be different. There's going to be different paths, different things. It's just not going to be fun. And one fun thing you can do with in-process is user-defined functions just by passing over function pointers, which is a very scary thing for many database architecture people, but it is possible. But it can also be quite difficult to make an in-process data management system because suddenly you're running a database engine on like somebody's phone or somebody's laptop, and like the hardware quality becomes a bit random, and that has some super interesting implications on how to design a system where you actually have to distrust the hardware it's running on. I'll come back to that later. You can't really. Crashing is bad because, well, if you have like a daemon like Postgres and a database sort of thing crashes, then it's not really a big deal because very often the daemon will just restart and nothing really happened. If you're an in-process database management system and you crash, you take whatever is hosting you, whatever process is hosting you, you take that down with you. It's not ideal. People are going to shout at you. There's a lot of like technical limitations, like you cannot use memory mapping, you cannot use signal handlers, you cannot use locales, you cannot use error. Like there are a lot of interesting sort of tiny nitty-gritty details. And while there is a super obvious way of representing arrays of numbers like integers or floating point numbers in memory, like there's like C arrays, which are what your CPU is also good at interpreting, which is why people use C arrays everywhere. It gets a bit more hairy when you talk about strings. Strings are quite a curse because everybody makes a different. There's like C strings, but those are pretty bad. And then there's 100 other ways of representing strings. And it's not fun, especially not if you're talking about arrays of strings. There's like 50 million different ways in which you, can represent those. So you have to, figure out something there. Again, arrow is a way out of this, a potential way out of this. So you want to make a new DBNS. I hope I have made that point. So we need a in-process OLAP. That's going to happen. And then in 2018, back when we started thinking about this. Oh no, it's not true. We didn't start about it. When we started thinking about this seriously, we made this beautiful slide I have here on my old analog TV. that what we wanted to do with our new system. Like we wanted to have environment awareness, where we say, okay, we'll do like cooperative, like resource management, because we're not the only software that tries to run something on this machine. We want to be able to like pause query execution, all these things. We want to do self-driving, because it's obviously we can't have a DBA in these like in-process things, because there is no DBA, it's just users. And as I mentioned, we're running on rando hardware quality. That so we need to make all these interesting things where checksumming during scans of data, all these wonderful things. What we kind of neglected to think about was that before we can do all these interesting things, there's actually quite a lot of work of building a new database management system. So we are at the moment still very much in the make it work first phase. But the result of that is that we have a new entry in the chart I showed you earlier, because we have DuckDB now. So DuckDB is the system that we're working on, and it is the first custom built in-process OLAP database management system. So what is DuckDB? Well, DuckDB is a database management system. So, you can insert, append, delete, add data to it. You can run queries. It runs SQL. It runs normal SQL queries, actually quite complex SQL queries. It is written in C++11 and just normal C++ code. And there's some special things, like DuckDB has 0 external dependencies. Because while dependencies are okay if you're writing an application, dependencies are really not cool when you're writing a library, because all your dependencies become transitive dependencies of whoever tries to use you, and that's going to be fun if they try to integrate. So DuckDB has no external dependencies. Because it is integrated in whatever host language, the APIs to the sort of hosting language become a bit more involved, and we have written APIs for a large amount of language. So we have C, C++, command line interface, we have Python and R. Those are client APIs that we heavily focus on. We have Java, we have Node.js, we have Rust, we have Go, we have like a lot of things. Julia also. And basically what this means is if you, for example, use Python and you want to talk to DuckDB, you kind of say import DuckDB, and then you start it up with this command. And what happens is that the DuckDB database management engine will actually run within that very Python process. And this is if you use SQLite a lot, it's going to be known. But for the first time, this is a bit mind blowing, because I was like, yeah, where's the database? Well, it's there, it's running, it's there, there's nothing else to do. It's pretty cool. Yeah, DuckDB is, because of this problem that we cannot really crash, it's extensively tested, and it's open source and available under the MIT very permissive license. And it's been quite a success. We have about 100,000 downloads each week for the system right now, and this is of course rising constantly. So just some sort of high-level overview of how DuckDB works. Well, it is using a columnar data representation. That makes sense for analytics, but it's not using a columnar execution engine. It uses a vectorized execution engine. What does this mean? Well, it's kind of this hybrid between a tuple at a time and a column at a time execution engine, where we run, well, all the operators run on a small fixed size subset of data at a time called a vector. For example, the vector size in DuckDB right now is the default is 1024 rows, but you can change that if you want. So it's a vectorized engine, which means we have a query plan. We built pipelines out of the query plan. They are interpreted plans that we then run. So it's not using a JIT compilation or anything like that. It's just a vectorized engine, which simplifies things a lot. DuckDB has MVCC, so we use I'm coming back to that later, we use a special version of MVCC that's optimized for analytical tasks. It uses a single file storage format, which is important because, again, this what I mentioned earlier about people emailing database files around, that's not a joke. That's what people actually do. They asked us to support this, so we said sure. And I mentioned it's written in C++, and it uses a heavily patched version of the Postgres parser. So if a query runs in Postgres, chances are quite high it will also run in DuckDB. It's been quite successful. We have had some success on Hacker News. So this is kind of funny. If you've been there a couple of times, then you start figuring out what the trick is to get on the top of Hacker News. Ask me for details if you like. But yeah, so that's kind of how DuckDB works. And let me just show you a brief demo. Let's see. I'm crazy enough to do a live demo in a lecture. So basically, I'll just open a terminal here. So I don't know. There's been a new release today, so let me just install that. Let me just install the latest DuckDB. So now I've installed DuckDB 034, great. And now I ignore all these warnings. And now in my Python, I can just say import DuckDB and basically say, okay, DuckDB now. And now I have a running DuckDB instance. I can do something like can execute select 42. This is just going to give me 42. This is a full-fledged SQL engine that's just running right there in your Python shell. And if I exit my Python shell, it's gone again. In this case, because I've used a in-memory database, but of course you could also put it in the file, in which case it will not be gone. Continuing with the slide. So what are some major milestones we've had in DuckDB? DuckDB has inter-pipeline parallelism. So basically we have a morsel-driven parallelism method where we look at your query and then automatically figure out how to parallelize your query using morsel-driven parallelism, which basically means that all the operators that are materializing operators, for example, like aggregations or join, so on and so forth, they actually are aware of parallel execution and are able to efficiently parallelize your query. We have developed a novel vector format, in-memory vector format, to support compressed execution and nested types. It's something I will go into a bit more detail in a bit. We have optimized a multi-version concurrency control to work really well for OLAP style queries. That's also something I'm going to talk a bit more about in a bit. DuckDB also has a log-free buffer manager, is able to propagate statistics through the query plan. So we are able to basically take any kind of statistics like min-max on input data, propagate those all the way through the query plan, and then are able to use those propagated statistics in the optimizer to, for example, eliminate entire sections of the query plan because they can never happen or something like that. You can also use it for type selection, like physical type selection. We also have, as I mentioned this, we have quite comprehensive SQL support in DuckDB. We can do subquery folding, which is something is quite noisy. Is that me? Probably. We can do subquery folding, which means like arbitrary subqueries are actually not run as subqueries during execution, but are turned into joins. We have recursive common table expressions, which is, if you're not aware of recursive common table expressions, it's a fun way of turning SQL into a Turing-complete language that is really, really bad, but some people do it anyway. And then there's a lot of other stuff like collations, like for multiple character set support. We have decimals, arbitrary, not arbitrary, but quite extensive decimal support, a window function support, hundreds of scalar and aggregate functions, and so on and so forth. The project is pretty huge at this point.
I have a question.
Yeah.
So, sorry to interrupt. Can you explain a little bit more about the loading stage, how DuckDB works with the data? So it operates as a library in the Python process space or whatever process space.
Yeah.
So the files for the query execution, is DuckDB loading files from, say, CSV, and then you transform it to an in-memory vectorized format, so there's a loading transformation stage? Or is it operating with ephemeral in-memory data structures in the host language, or both?
It can be both. So DuckDB can directly run on CSV and Parquet files. We have the native Parquet support. If so then we just run the scan operator directly on the CSV or Parquet file.
I see.
That also works, for example, directly for pandas data frames. So if I have a pandas data frame in my Python shell, I can point DuckDB to this pandas data frame and say, now run a query on this, and it will not actually do a conversion step. It will only do, it will run the scan directly.
But the pandas data frame might be laid out in a different format than what you expect for DuckDB's physical operators.
That's all right. We'll stream over it. It's like we can do a streaming sort of conversion of individual.
I see. So does that mean you have multiple physical operator implementations for?
We have, for the scan, we have like 15 different scan operators, depending on the specific input format. What you can of course always do is you can take the scan for whatever input format you have, and say create table as select both from my scan operator, and then we'll create DuckDB native data structures to hold the same. Yeah, and those could be either in memory, where they're ephemeral and they go away when you exit the process, or they can also be persistent, where we then write to the database file and they have MVCC and the whole.
I see. So just to clarify, so what is the persistence layer of DuckDB? Is there a managed kind of abstraction on top of the file system, or?
Yeah.
Is there a catalog?
I'm sorry? Is
there a catalog?
There is, yes, there is. So we have the single file data format that mentioned here. This data format is custom, something we invented. It's has metadata about what tables exist and so on and so forth.
Okay.
And then it has each table has different row groups, and the row groups for every row group, the different columns are laid out into these blocks.
Got it.
It's just a serialization of the database, and it's transactional, so you can
got it.
You can run checkpoints. You can.
I see.
There's a separate val that we write to before we checkpoint. So it has all these things, but you don't actually have to use it. So this is, I think, special about DuckDB is that indeed most other systems, they have like one scan operator, right? For the data file, like Postgres has a scan operator for Postgres' file format, like nothing really else. In DuckDB, we have decided that all scan operators should be created equally. And we actually also use this, and we have actually a plugin API for that. So you can actually write your own scan operator on whatever data format you have.
I see.
And then it will be exactly the same from capability wise. Like it can do push down, it can be whatever things. It will be exactly treated the same way like our internal scan operator. And this is quite powerful because, for example, we recently released a scan operator for like Postgres and SQLite files. And with those operators, you can just directly point DuckDB to a SQLite file, for example, and run a query on that. Yeah, as I mentioned, we also have it for data frames in R and Python, Parquet files, CSV files.
Okay, excellent. So the last question is, do the data files need to fit in memory, or is DuckDB disk aware?
It's disk aware. The data files can be as large as you want.
Okay.
Whatever. And we're actually currently working on something exciting there as well, because we're also working on making all the intermediates created by all the operators disk aware.
So you can spell the intermediates too.
Yeah, and that's I think a novelty, like pretty novel in like analytical engines, because most of them assume that the working set like a hash table will fit in memory. But in DuckDB, since we say, hey, we also need to run on like some weirdo IoT device, we probably cannot assume that there's 10 terabytes of memory sitting around. So your data file can be as big as you can run DuckDB on like a terabyte of Parquet files, no problem.
Excellent. Okay, sounds good. Thank you. Let's continue.
Yeah? Great, thank you. So just briefly, the vector format. So the vectors are this core unit of data. It's called a vectorized engine for that reason. It's like a subset of a logic column of data. The table is basically a list of vectors. And what we kind of want to support is compression, and we also want to support nested types. Nested types are structs and lists and something like that. So this has been quite a design process to get the vector format right. And vectors are not equal to vectors because we do want to have different ways of representing vectors. And the reason we want to have different ways of representing the same, like the logically same vector, is because we want to be able to run queries directly on compressed data. Let's say, for example, you have RLE compression. You don't want to have to expand this RLE compression just to run a query. You kind of want to run the query directly on the RLE with Meta. So as I said, naively, you would decompress and scan, but the problem is that it kind of blows up your data set, and therefore, it makes data that would normally fit in memory no longer fit in memory, and it gets you in all sorts of hurt. Engine explosion. And the challenge with operating directly on compressed data is that there's many different compression methods, there's many operators and functions, and there you get a code size explosion and an implementation effort explosion if you were to implement all the operators for all the different compression methods, right? That makes sense. So what we came up with was this canonical idea of canonicalization, thank you, that assumes like, yes, the vectors can be stored in many, many encodings. You can have hundreds of different encodings. And the operators are free to implement whichever one of those they want, but not every operator has to do this, because there's operators where it doesn't matter. And they all have to support this one canonical format. And if the operator doesn't support the specific compression format, then it will just call a canonicalize operator on the vector and will be able to operate that. And that way you can basically make the specializations for specific compression formats only for where it really matters in the execution engine, and everything else like operates on automatic mode and you don't have to care about it. It's quite a powerful concept. And the format we have come up with for this is called the Orification. That is a reference to Ori Erling, who is pictured on the slide, who's been quite helpful in designing this. So what we do is we have the vector that consists of the canonicalized format consists of a definition mask, which basically tells you where the nulls are, contains of a selection list, which allows you to kind of do offsets in an unchanged data vectors, and of course the data itself, which is a C array of plain values. And with this representation, you can basically represent most compression formats quite cheaply without actually having to do this unpacking into a flat vector every single time. So here's an example. Say you have a RLE, which consists here of 10 times 1, 42 times 5, 43 times 4, 1 null, and 1 time 11. And if you were to unpack this, you would have quite a lot of data. But in the Orification, we basically get this 3 elements, namely the define mask, which here is all true except for the 1 null there. You get offsets, which is basically the selection list into the binary, into the data array. And then we have the data itself, which is just 10, 42, 43, 11. And this is quite cheap to do, and it allows you to deal with compressed execution in a vectorized format without having to deal with this code and implementation effort explosion, which is important if you say running a small data management company with 10 people and not Oracle. The second thing I wanted to talk a bit about is the MVCC. And so what we use in DuckDB is something that is sort of inspired by what Hyper does. There's a paper about the MVCC in Hyper. But we've kind of changed this. And the way this works in Hyper is you have this, for each tuple, you have the undo, like you do the change immediately in the data, but then you have undo like previous version pointers that allow you to revert if the transaction aborts, and also allow you to do snapshot isolation. And the problem is if you do this in a row store kind of style, you get a lot of overhead if you do batch updates, because the problem, one of the observations in analytical data management systems is that your updates are also batchy, are also bulky. They're not like row-based updates. Mostly they're like big updates, like delete from orders where order time is smaller than this. This could delete like 40% of your database. So if you had to do undo pointers for every row individually, this would be quite a lot. And so what we did is we changed this to keep the undo version only per column chunk, which allows you to do undos and versioning per on a much higher, like in a much lower granularity, and therefore better for analytical use cases. And this you can see here's a small benchmark. If you do is a small benchmark where you do like many single column updates on a table with a single column, and you can see that okay, for this very simple change, Hyper takes 24 seconds and DuckDB takes 0.7 seconds. And this is a huge difference, as you can probably see. And this has to do with the fact that we do the MVCC also on this bulk level, on a columnar level instead of a row level.
I should point out that, sorry, Hannes, they use the comma instead of the period in Germany and in some parts of Europe. So that's a decimal point over there, not a comma.
Oh yeah, that is true. Yeah, I'm sorry about that. I think it's automatic if you have your local settings to Europe in my yeah, you are correct. This is a decimal. So here you can see that this makes a huge difference if you have this kind of analytical style updates. It gets even worse if you have 100 columns and you update a single column, then Hyper takes 149 seconds and DuckDB still takes 0.72 seconds because obviously we have only updated a single column. So this is the kind of thing that we spend a lot of time on. And yeah, so what are we going to do next? Well, we're spending some time on cardinality estimation right now. We're spending some time on UDFs. That's ongoing. What is blocking us from doing a 1.0 release is that we want to finalize our on-disk representation, so it becomes backward compatibility from then onwards. And it's kind of terrifying to have to finalize a disk format when you know you're going to be bound to whatever decisions you make till all eternity. That's kind of terrifying. But basically, we want to make the basic functionality a bit boring, that like it works and we don't have to think about it, and then go back to the interesting issues.
So
for example,
there's a question on chat from Mohed. Mohed, do you want to unmute and speak?
Yeah. So just wanted to ask whether the canonical vector format, does it exploit any hardware level parallelism that is available on the hardware that the process is running in during the processing of the query?
So you mean like multi-threading or something like that?
Yeah.
So that happens on a higher level. So the Morse-level parallelism will partition the query into separate pipelines that can run independently, and then we parallelize in the pipeline. So we do not parallelize on the vector format itself, but on a higher level. The vector format itself doesn't have to deal with parallelism.
Okay, thank you.
Okay.
So just to clarify, Hannes, that means the hardware libraries that you assume, or the hardware library the environment offers, is something that you piggyback on. So because you have this heterogeneous platform backends, right? You have to run on a phone, you have to run on a browser, on a laptop, or whatever else. You don't assume anything about the lowest level of the stack, right?
Not a lot. I mean, we have gotten DuckDB to run on like pretty esoteric things, like one of our team members got it to work inside the Intel SGX trusted hardware thing, which is pretty crazy. People have gotten DuckDB to run in WebAssembly on browsers. It's let's say the abstractions that are on the bottom there are just C++ API calls, right? I mean, like standard library. So
got it.
We don't really do anything crazier than that. And in fact, we spend quite a lot of time on keeping this stuff generic because we don't want to, we don't want to implement something like Linux specific abstractions that would hamper compatibility. We do try to prioritize compatibility over like highly optimized for one specific platform, and we got like validated by this accidentally because Apple just happened to bring out a new hardware platform, right? Like last year or something like that. And, DuckDB was running out of the box on it because, it really didn't matter. I recently had some fun on a hardware that was a 16-bit architecture. And it's actually quite funny if your int, suddenly becomes a 16-bit int. Lots of your assumptions are suddenly not really there anymore, but it did work.
Okay.
So that's kind of fun, yeah. Okay,
thanks.
Yeah. Okay, so the interesting issues back from 2018, and I really want to go back to that. It's been a while. Is this like user hardware thing, right? So basically saying, okay, what if the hardware misbehaves? And this is not a theoretical problem. We actually get bug reports sometimes where people clearly have broken computers, and they say, if I do this, my computer with DuckDB, my computer breaks. And we're like, yeah, because your computer is broken. It's just that no other software is maybe using it like this. Maybe nobody else is actually using all your memory, even though it's broken. So, and of the kind of different bits of hardware, like the CPU, it's probably safe because they usually have built-in checks. The disks, we do checksums on everything that's all the blocks in our file format. We have like hashes on them, so we know that that they're intact. The network, yeah, people are used to design around failing the network, but the RAM, I'm telling you, everybody trusts RAM way too much. RAM is actually shockingly unreliable. There are some interesting papers. For example, there's one from Microsoft where they just looked at the kernel dumps that Windows uploads to them, and looked at how many of those were caused by like random memory errors, and they're shockingly quite a lot, and also very shockingly many orders of magnitude more than the hardware vendors would assume they would be. So RAM is really something that we want to have another look at, and there's like these transient errors, which are basically bits just doing random things. Yeah, it's pretty cool that nobody has really spent time on this. So we did some interesting experiments. Student of ours did this, where we introduced bit flips in the memory on purpose, and then just look what happens. And you can imagine there's various outcomes of this, like system response. If it's an error, it's great. I mean, it's not excellent, but an error is okay. We can deal with errors. Like the system says, error 42, great. A crash is kind of okay, because yeah, I've made some memory bit flips are just like, okay, if this flips, this is like fault because you're chasing a pointer that is suddenly like not valid anymore, fine, you crash. There's also a class of errors that is a bit worrying, which is like the system suddenly gives wrong results. And this is particularly worrying if this happens during checkpoint, because then you make your wrong results persistent. So here's a chart that shows you SQLite running TPCH query 1. And on the x-axis, we have the memory fault rate, the simulated memory fault rate. On the y-axis, we count like how many times this particular outcome has happened. And you can see these lines, like the blue one is okay. So your blue one goes down because obviously more faults happen, so bad. The green one is the crashes, that goes up. That also makes sense because the crash probability is going to go to 1 eventually. The abnormal, I think it's also kind of a crash. But then there's the incorrect line. You can only not really see it on the left chart here, but on the right chart, you can see it. And you can see that there's this interesting bump there of the yellow line that is the incorrect results. So this is not just a theoretical thing, and this happens in SQLite, which barely uses any memory. And so this is going to be a much more bigger problem if you run this on an engine that actually uses memory like DuckDB. So we want to get back to that. Some ideas on how we could mitigate this. For example, we're thinking about checksumming intermediates in the engine, like hash tables. The hash tables are the biggest problems here because they are big and they stay in memory for a long time. So we wanna be able to make sure our hash tables are like not breaking. This also applies to vectors. For example, if you have a vector that's written by one operator and consumed by another operator, you might want to be able to verify that you've read whatever was put in there before. It's kind of important. And of course, the buffer manager that manages memory for your database engine also could check whether the memory it gives out is still behaving as expected. The only problem is that these. So first of all, yes, if you add these mitigations, the incorrect thing goes down, which is great. The only problem is that these mitigations are not free, and here is a log scale chart that shows you TPCH runtimes, and we still have loads of work to do to get the mitigations to be as fast as the versions with mitigations to be at least comparably fast as the normal version.
And it's a good question.
Yeah.
This is very fascinating. I don't think we've seen this issue in a DBMS context before. It seems like you guys are studying this for the first time here. And it makes a lot of sense for kinds of the device environments you're talking about. One quick question is, what is the state of the art for other programs that run on these devices? Because this issue will happen to every program that runs on the device, including user apps and other things. What do they do? Do the embedded systems folks not have built-in safety checks in their PL runtimes?
I don't think so. So interestingly,
wow. Okay.
So there is, of course, ECC mem, like servers have more expensive memory that has error correction built in, right? But I don't think iPhones have that. And And I think this is just assumed as like it just happens every now and then. It can have quite disastrous consequences.
So you're saying this is the stuff that leads to crashes with the apps?
Yeah. That's one of the possible reasons why apps crash, right?
Fascinating.
There was one context in which I've seen this was computer games, because they have to deal with all these overclockers, and people that overclock their systems sometimes also very often also break them, right? They overclock them to the point where they don't run reliably anymore. What does not run reliably anymore mean? Well, it means your RAM starts doing whatever, right? And so I've seen a blog post like years ago that I cannot find it now. It's quite annoying, where somebody described like, hey, they got their support like issue ticket rate down a lot when they started adding self checks to their game engine, which basically just every couple of frames was like, okay, I've rendered a couple of frames. Let's just run some check to see if the memory is still sane. Okay, it's still sane, continue. And that I thought was so fascinating, because it kind of triggered this and also our thinking about, hey, hang on, if they do this, we should probably also be doing this.
Very fascinating. So now you can give integrity guarantees on your query results.
Not yet, right?
That's where you're heading, it seems like.
We want to be able to at least give statistical guarantees and say, okay, the chance of this crashing because of a memory bit flip is like essentially 0.
Very cool. Okay.
Yeah. This is really fascinating. So memory like hardware second guessing, specifically memory second guessing is kind of something that I really love to come back on once we get the boring things out of the way. Conclusion: OLAP systems are better in process. I think that's one of my conclusions. Even if you're not building an in-process system, you should probably build one, because it really simplifies testing. Because if you can run tests on an in-process engine, you can run like order of magnitudes more tests than if you do this in client server. So pro tip there. And there are new challenges also when building in-process OLAP, like the cooperation I've mentioned earlier. How can you cooperate within the same process with other things that also try to achieve things? Get second guessing the hardware. I think this is a vastly under-researched topic, especially given that the IoT sort of revolution, or mobile devices, things like that, where we now also handle significant amounts of data, yet we have no way of dealing with errors. The bulk transactions I mentioned to you, like the MVCC that is able to deal with bulk updates, is super interesting topic. And one of the things that one of our PhD students is working on is this gracious out of core idea, where I've mentioned earlier that we are working on intermediates being able to go out of core when they don't no longer fit in memory. But traditionally, people then just switch to entirely different implementations, like, oh, fine, the hash join isn't working, let's do a merge sort join. And that I think is wrong, because it kind of abandons all the work you have done up to this point, and it switches to this like vastly slower thing. So what we really want to do is like still use the memory we have, but just be able to spill a parts of a little bit of the hash table we're currently not fitting in memory to this. And it's super fascinating, I think, as well. That's it. Sorry for going slightly over time. There's much more to talk about. There's on our website, we have a section where there's like more lectures, podcasts, like slides, like the whole sort of thing. If you want to learn more about DuckDB, you're of course always happy to ping us. Welcome to ping us. We're happy to see things pop up on the issue tracker, or even pull requests if you're so inclined. So thank you so much.
Great. Thank you, Hannes. Audience, let's give Hannes a round of applause. We do that virtually, but I don't know if that works on the button. So I'll just give you a coffee icon and I'll clap.
Okay.
More questions from the audience? That was a great talk. Thank you so much for explaining all the trajectory and the vision and the technical implementation choices, design decisions.
It's really fascinating. Both, right? It's like,
yeah,
here's the vision, and then here's some funky details that you run into while chasing the vision. It's like,
audience, more questions? Okay, I have some questions, but I want to give the audience a chance to ask more too. So I can start. So the situation with in-process DBMSs is kind of reminiscent of back in the 90s, OODBMSs, object-oriented DBMS, there was this whole community, or from the PL side and the compiler side, they said, we don't need RDBMSs. We don't need a separate engine, separate process. We will just allow you to scale arbitrary data structures and make them run efficiently, make them disk aware. Now, of course, this OODBMS versus ORDBMS battle ended with the RDBMS folks winning, right? And they said, well, OODBMS, you quickly run into the issue of dealing with Turing complete programming languages. How do you parse out what is going to scale, what is not? I think here we don't have that problem because you're using SQL as your interface, right? And we very well understand SQL and the data structures that go behind SQL code. What is your take on? Much better than what we did for OODBMSs.
True, okay.
So, it seems like also the emergence of IoT and laptops and all of that in the last couple of decades has made it much more appealing to have these sorts of in-process systems, right? And back in the 90s, it was not the case. I don't think laptops were that common. And IoT, well, it was not even probably at universities, but now it's ubiquitous. So what is your take on this landscape of cloud versus edge in this scenario right now? Because there is this debate that, oh, edge computing, we want to put all these things on these devices, but we also want to retain capability that's more advanced, more compute hungry in the cloud. DuckDB seems to be like, you want to put as close to the device as possible, but of course it's not like you cannot put stuff where you want. So what is your take on this, both on the trend of these in native data structure scaling from the OODBMS kind of legacy, and also this new trend of cloud edge splits?
Yeah, I think, yeah, it's super fascinating. I mean, I haven't thought about the OODMS thing for a while, but I think one thing that we see a lot is that it's like these data science workflows that are, so first of all, the OODMS is problematic. It's problematic for similar reasons than like the graph databases, right? They have the exact same problem because they have these pointer chasing nightmares that are just never going to work for OLAP style queries, right? Because, because whether you're running like a graph query or you're doing like a complex query in an OODMS, you just have these endless pointer chains that you will just not win against random access there. So that's why I think this hasn't worked out. It's, I think, the same reason why I think many graph engines out there will struggle to ever scale. So with regards to the landscape, I think what DuckDB is, what we have recognized is in like data science workflows, that there are a lot of stuff that was essentially relational but was using something else. And so DuckDB was also kind of designed to be an engine for these kind of use cases where you just want an engine that does relational style queries while not being very obtrusive. So I think it's coming like from the similar idea than the OODB thing, where you're saying we have something in process, we want to scale data structures, but maybe with a bit of restriction to data science use cases that are often, I would say, quite tabular and quite relational in nature, which makes it easier, like more tractable to design efficient data structures around, which we know we're like, okay, this probably should be vector, probably should be columnar somehow, and you know, probably want some engine that has a low tuple per cycle ratio, right? So this I think is a bit of an easier sort of chunk to chew, if you want. With regards to the edge devices versus central cloud, I mean, there's nothing stopping you from using DuckDB in cloud, and I know people do. We have added some features recently that might be kind of interesting to do both. For example, you can totally run DuckDB on like a phone, right? In fact, we have done an experiment with like running DuckDB on like the first generation Raspberry Pi. Like it's just like a piece. It's not a very great compute thing, but it's faster than running SQLite on the same thing on like a giant server, which is kind of funny, on TPCH, which is unfair for SQLite, I admit. But we have added some features, for example, to do aggregate state export. So you can do things like quite cool pre-aggregation on device, take the results of your pre-aggregation, ship them out, let's say using Parquet, and then use a central node to finalize all the aggregations, pre-aggregations you got from your you know, distributed devices. So I think that's going to be the one interesting answer there, is to say, why not, if you're running the same database engine on both sides, you can actually do like very clever things where you, yeah, for example, do your pre-aggregation locally, keep the data on the device. Maybe you do some sort of pre-compute that allows you to reduce the data amount that you have to ship. I think that's going to be the answer. Like, imagine you have like a traffic camera, you know, it could stream all the data to a central location where you run a clever algorithm, but maybe that's not necessary. Maybe you can use DuckDB together with whatever computer vision algorithm that you want to do, and then only, you know, trigger the results of that compute upstream. I think that's totally feasible.
That makes sense. That's fascinating. So that gets into this territory of federated analytics. Federated ML is already very popular in many device settings. Apple and Google are using it, but federated analytics is also catching on. I think this makes a lot of sense. You do parts of the computations on device and parts in the cloud. So does DuckDB is also aiming to build a cloud native system then?
Well, there are people that are thinking about that. We are. I'm sorry.
Which people?
I'm not sure. I'm not sure this is officially.
Okay.
But I mean, this is certainly something that we have discussions with people about this. I think it's interesting. I think what is interesting there is DuckDB is very good at parallelizing queries. We can run on hundreds of cores. We can go up, you know, to like terabytes of memory, no problem. And it's quite fascinating how many data sets actually will run on these things. And you can get cloud boxes that have like these kinds of characteristics, right? So it's quite, what many people forget is you can actually rent like a 10 terabyte RAM box, no problem, on Amazon, right? This is not a problem. So why would you start dealing with the sort of this nightmare of running a distributed system if you don't have to? This is something that has always been fascinating to me, is that, you know, also the academia has been kind of full steam ahead on distributed analytics for the last 20 years. And like starting with Hadoop, I guess, and then in the meantime, like single node became so incredibly powerful, and nothing has really happened in terms of like attention to it. So we also try to bring attention back a bit to single node and how powerful it is. It is especially interesting if you can just rent these kind of computers for a short time. You don't have to buy the €100,000 box yourself. You can just use it whenever you need it. I mean, that
makes a lot of sense. Yeah, I think there's a market reason why that was the case. The very extreme high-end data scales, that's systems that's the highest paying customers. And so now you have the situation of huge number of small paying customers. So that's a market argument there. So coming back to this question about heterogeneity of platforms and backends, do you also work with hardware accelerators or GPUs and FPGAs and all these ASICs, like on the phones there are ASICs, or is there not enough of a kind of advantage for running relational computations on those devices, and so you're not targeting those sorts of backends?
The latter. I think there's no point of running relational style queries on accelerators. There are a lot of good ideas of running stuff on accelerators. I think if you have like a neural network, sure, you know, go.
Okay,
but
so
anything that like a relational engine does.
Okay, so you think the arithmetic intensity is not too high to be bothered about that?
It's gonna be IO bound anyway, and then it's like, okay, so now I get to shovel everything into my GPU, which doesn't really.
Or ASICs on the phones.
I mean, ASICs on the phones, yeah. I think that the FPGA crowd is interesting there, because there have been a ton of people that have tried, and then, you know, they run experiments against Postgres and say they're faster, which is like, okay, but maybe run this on something, like run this against something competent. I haven't seen it yet. I mean, maybe I have to eat my words in 5 years, and it's entirely possible, but so far, no.
There's a lot of action in that space. Data flow design, hardware accelerators. There's a lot of action.
But they're not looking at relational operators. They're looking
Some
at
of them are.
What?
Some of them are.
Some of them are. Well, all the best.
Let's see how it'll be fascinating to see how it evolves. Okay, great. Sounds good. That's all from me. Any other questions from the audience? I see some folks are still hanging around. No, okay. Okay, great. So then I guess, Hannes, we're at the top of the hour. So thank you again for visiting and sharing about your thoughts. This is spectacular stuff, very exciting times. And students now see that core database, relational database systems implementations is also very fast evolving now with all these dramatic upheavals in computing landscape. DuckDB is an exemplar of one of those exciting directions of growth.
Thank you so much for having me. Great questions. Thank you, everybody. I did enjoy it.
And say hi to everyone there as well, Hannes. Thank you again.
I will. Thanks, everyone.
Take care.
Bye-bye.
Bye. Thank you to the audience for joining.